Okay, so the first generalization is the fundamental theorem of calculus for curves. Really, this is going to be the only one that we prove, just because it's the only one that I want to prove. The other one's a little more complicated, but it shows that even for this, in this situation, it just goes back to the fundamental theorem of calculus. So let's begin with this. Recall line integrals of vector fields. If C is a curve with smooth parameterization, R of t equals x of t, y of t, z of t, for for t going between a and b, and the vector field is given by the components f1, f2, and f3, then this is just this part right here. This is just how we computed line integrals of vector fields. I've written this in 3 dimensions, but similar things are true in 2 dimensions or higher dimensions. When I prove this theorem, I'm only going to do it for 2 dimensions just because, as you'll see, I'll run out of room if I do it any higher than that. So let's begin. Let's prove this. Let's first say what it is. If R of t is a nice parameterization of a curve, again, basically we mean piecewise smooth. Smooth means that you can take derivatives of the x of t and y of t and the r of t. So you can take a derivative of x of t, you can take a derivative of y of t, and r prime of t is never equal to 0. That's the kind of stuff we're going to see. We're not going to look at anything where you don't have that, but I just need to say it. So R of t is a nice parameterization for a nice curve in Rn. T goes between a and b, and f is a nice function. Again, that just means basically that it's continuous and you can take derivatives of its components. Then the line integral of the gradient of f is equal to f of r of b minus f of r of a. So notice how this is very similar to the fundamental theorem of calculus. On the left-hand side, we have an integral of a derivative, and on the right-hand side, we have f evaluated kind of at the endpoints of the curves. And that's very similar. That is similar in form to this part of the fundamental theorem of calculus. Okay, so how can we prove this? Well, we want to compute the left-hand side. According to this is just the integral t equals a to b of fx of r of t. F sub x means the derivative of f with respect to x. F sub y of r of t dotted with x prime of t. And now you see why I can't do this in 3 dimensions because I'm already running out of room. Dt. But notice that by the chain rule, what is this integrand equal to? All this is the derivative of f with respect to t when you're evaluating it at x of t, y of t, dt. That's all the chain rule says. That's what the chain rule says when f is a function of x and y are both functions of t, then f prime of t is equal to exactly this part right here. Okay, but this is just equal to the integral t equals a to b f prime of r of t, where f prime means the derivative with respect to t. Okay, so now f prime is a function of t. This is a scalar valued function. Now we apply the fundamental theorem of calculus. This is f of r of b minus f of r of a. And again, we're just applying the fundamental theorem of calculus. F composed with r of t is a real valued function of one variable. So we are in the setting of the fundamental theorem of calculus, and all we're doing is applying the fundamental theorem of calculus. That's all we're doing.